So this is the Nintendo. We talk about this as the NES, the 8-bit Nintendo. This is a clip from a video series talking about writing an NES emulator. Now that's the process where you take games that play on one computer, in this case, the Nintendo Entertainment System, and use software to write instructions so that those same games, those same programs that expect to talk to that particular CPU can run on any other computer system. That this emulator he's built up has a whole lot of pieces that talk about CPUs already. We've got this big area over here in the top right, which is showing the particular bit of sprite memory. We've got a huge array of hexadecimal values that are showing us values of memory that are written. 1, 2, 3, 4, 5, 6, 7, 8. We have a section down here that shows us the current values of particular registers, including the stack pointer. It shows us what the current clock step is, and even the current lines of assembly or machine code that are being executed by the game. So we can pause these and take a look at them. Fun here, and he draws the CPU. And then he goes into write this strange number here. Really, this CPU is a 6502. Let's see about the details of the CPU, because this is the IB computer science stuff that we're talking about. Right now, we have a CPU and we have a bus. Right now, we have a CPU and we have a bus. Both of them are key components of the IB computer science model. This CPU, which is a 6502, you can see that it has two little paths to the bus. One of those, it has marked with an A, is only one direction. It's only going to put data onto the bus. And the other one, which is marked D, is two-directional. It can put data from the CPU onto the bus or from the bus onto the CPU. These two are the memory address bus and memory data bus from the IB CPU model. They're shown here as being little components that connect to a larger bus. That's one of the abstraction things that the IB CPU model does, is it takes out the notion of a large bus that spans the entire CPU and focuses on just these two little elements. And so what's next? He draws out 3 mystery boxes, and then he goes through and writes these hexadecimal values on the bus. Is that when we talk about getting values from memory, we think about that as just being RAM. But in smaller computers or in any place where there's any sort of fixed storage, every location in memory is defined by a hexadecimal number, whether it's part of 1 chip or 10 chips or 15 different chips. So those hexadecimal values are still just the way of saying this location of data, whatever that data happens to be. And so now he's gone through and taken that large range. Why is it 0000 to FFFF? Because the 6502s has a 16-bit data bus and an 8-bit address bus. The 0000 to FFFF is giving us 16 bits of values to work with. But if you look at some of the places where we're going to actually put addresses in, we might have smaller values. So now we have the notion of RAM. Part of the IB CPU model, it's a key part of the whole von Neumann architecture. The idea that we have one set of logic gates that can do various operations, and we have one giant bit of memory that we can read to and write from and write to as we see fit. On the NES, that's 64K is the maximum amount of size we can deal with there. Now he's showing off something that I think is way beyond the IB level, but is really pretty important. This CPU is sold by a company in order to make money. We might buy it as a component of a larger bit of retail product, but somewhere along the lines, engineers have to buy 5, 10, 15, 20, 100,000 of these things and build systems that they go to. So what we're looking at here is the pinout. This 40-pin version of the 6502, much like an Arduino or other sorts of things, has a bunch of various analog inputs, control lines, digital inputs, digital outputs. It's a way of saying which of these little physical wires are going to carry the data from the CPU. And what's this here? Here in the manual, in the instruction manual for the CPU, we see, reading down the list, what do we see? Clock generator, timing control, program counter, instruction register and decode, stack pointer. What's down there beneath my little processor status register, the accumulator. These are all components that are crucial for any CPU. And in the IB model, they're all bundled in as part of the control unit. The clock, timing control, even the program counter, which keeps track of what our next address is. None of those things get specifically called out in the IBCS model, but we can think about them as all being a part of the junk drawer inside the CPU. The IB CPU model really doesn't talk about registers outside the MAR and the MDR. So here's a great rundown of the stuff that we just talked about as the control unit, as the key parts of the 6502. All of these things, the accumulator, the X and the Y registers, the stack pointer, the program counter, the status registers, all of those are just registers that can hold 8 bits of data. The only thing that makes them different is how the structure and the architecture of the CPU is designed to read and interpret values from those pieces. Let's talk about the status register real quick. The status register is a way of trying to keep track of a lot of the questions that need to come up in a computer program, such as we're doing a comparison. If this number is negative, okay, how does the ALU tell whether a number is negative? Well, part of the structure of this CPU is that if it performs any calculation where the value being returned winds up being less than 0, it will flip a single bit somewhere in the status register. If you want to have a if statement that checks about whether the result of that computation was negative, rather than having to actually read the value out of register X or Y, we can just read the particular bit out of the status register. It's a way of doing a comparison and saving a lot of computation time because we don't have to actually write that value into another bit of memory and read it out in a later calculation. We can just say, do the calculation, record only the status bit, and then we can move from there.